coming. So welcome everyone to the seminar. Today's speaker is Koichi Hamaguchi from Tokyo University. He did his PhD, or he obtained his PhD from the University of Tokyo in 2002, and then went on for postdocs at Tohoku University and at DESI, became their staff member, and then since 2006 he is associate professor at the University of Tokyo as a faculty member there. And he's very active in astroparticle physics and cosmology, and today he will tell us about Supernova-scope for the direct search of supernova axions. So please, Koichi.
Yeah, so thank you very much. So for the invitation, I'm very happy to give a seminar here. So yeah, the title is as introduced, Supernova-scope, and this work is based on this rather large collaboration, 8 authors, 3 of them. By the way, can you see the pointer?
Yes.
Yeah. So 3 of them, the Koichi, Chimura, Yasuhiro, and Koji, they from Tohoku, they are experimentalists. So we asked them to discuss the experimental part, and then the others are theorists, 3 from Tokyo and 2 from Shanghai, TDDI. Okay, so let me start from this one, Supernova 1987A. I think this photo is quite popular. That this right photo is the before the supernova, and then the left one is after the supernova explosion. And before this light came, a few hours before, the neutrino event was recorded in Kamiokande. Within this about 10 seconds, about 10 or a little more neutrino events were recorded. The neutrino burst was recorded. So what if the next nearby supernova occurs? Hopefully in our lifetime, or maybe in the next generation, I don't know. Of course, then we could learn a lot about the neutrino and supernova, like the case of 1987A, but maybe we can learn more from the next nearby supernova. So today's main message, actually, this is a summary slide. I will end with this slide at the end of the talk. This is a summary slide. The main message is as follows. So if a nearby supernova occurs, like a few hundred parsec from the Earth, then not only the neutrinos, but maybe a huge number of axions also arrive at the Earth. And those supernova axions may be detected by what we call Supernova-scope, axion Supernova-scope, with the help of pre-supernova neutrino alert. Actually, a similar idea was discussed by these papers, but we did a little bit more detailed analysis with the proposal of this detector. Then we also discussed the prospects, that the expected number of events for such as supernova axions, and found that in an optimistic case, we may be able to detect order 1 or 10, hopefully hundreds of supernova axions. So I will discuss the sensitivity curve at the last part of my talk. So this is the main message of today's talk. And if you already get the idea from this figure, then the rest is just, how to say, the details. But the story, I think, will be very simple. So this is the plan of my talk. I start from the mini review of axion. I'm not so sure if it's necessary, but I thought maybe there are some students. So I give a brief review of axion physics. And then in the main part, I talk about the supernova scope, and then summarize. Okay, let me start from the axion. So the motivation of this study is the axion, and motivation for the axion is the strong CP problem. So in the standard model Lagrangian, one can write these 2 terms for the gluon coupling and the quark, imaginary part of the quark mass. And the linear combination of these 2 dimensionless parameters, like this one, theta bar, is a physical quantity, but its experimental value is essentially 0. It's known to be less than 10 to minus 10. But these two are the dimensionless parameters, and especially the quark mass, in some sense, should have a non-zero complex phase to explain the CKM phase, Kobayashi-Maskawa matrix. So it's natural to expect this theta q is non-zero. Then it's very unnatural that these two independent parameters cancel out to give essentially zero. So I think it can be regarded as the most serious fine-tuning problem in the standard model. So the Higgs mass or cosmological constant, they are in principle may be explained by the anthropic argument, but the strong CP problem, I think, cannot be explained by the anthropic discussion, at least in the minimal setup. So, and then this strong CP problem can be solved by the Pichet mechanism, which predicts a light particle axion. So essentially, in this mechanism, this theta term is replaced by axion field. So theta is now A over FA. And this axion field gets a non-trivial potential because of the anomaly. And at the minimum of the potential, this theta bar is automatically zero. So without fine-tuning, this becomes zero. Dynamically, the strong CP problem is solved. And moreover, the axion can be the dominant component of dark matter depending on this FA. So it's a very attractive candidate for the physics beyond the standard model. And there are two conventional models. One is KSVZ model and the other is the DFSZ model. And there's also variants of many variations of axion models. One of them is the Flaxion model, which we proposed several years ago to explain also the flavor structure of the standard model. But in any case, in all cases, we have one complex scalar field called Pichet-Quinn field, and which is charged under the global U1 symmetry. And this global U1 symmetry is spontaneously broken by its potential. And because of the spontaneous breaking of the U1 symmetry, there's a Goldstone boson, and that is the axion. So at this level, axion is completely massless, the Goldstone boson. But because of the QCD anomaly, it gets a non-zero potential along this phase direction. And at the bottom of this non-trivial potential, this strong CP is automatically becomes zero by the vacuum expectation value of the axion field. And that's how the strong CP problem is solved. So in the following, I sometimes refer to the KSVZ or DFSZ models, but basically the axion is just a Goldstone boson associated with this complex scalar field phi. And axion's coupling is determined by the decay constant Fa. So the axion coupling to gluon is inversely proportional to Fa. Axion coupling to photon is also inversely proportional to Fa, and also coupling to fermions, quarks, and leptons. So there are some order one parameters like CF, C, gamma, gamma, and so on, depending on the details of the model, but they are basically order one parameters. So roughly speaking, the coupling of the axion to the standard model particles are just 1 over Fa. Also, the mass is determined again by this decay constant Fa, and it's also inversely proportional to Fa. And this Fa actually is constrained to be very large compared to the electric scale, like 10 to 8 or 10 to 9 GeV. And it turns out that the mass of the axion is very small, like milli-electron volt or electron volt order. And also the coupling to the standard model particle also suppressed by this 1 over Fa. So they are very weakly coupled. So overall, roughly speaking, all the parameters, the couplings and masses are essentially determined by this decay constant Fa up to order one model dependent parameters like this one. And there are various constraints on this axion decay constant parameter Fa. So it's the plot taken from particle data group. This is 1 GeV and to 10 to 18th GeV. And this shows axion mass, so it's inversely proportional to FA. So from 10 to minus 11 electron volts to 10 to 6 electron volts. And these blue ones are the constraints, and there are also hint here. So there are astrophysical constraints, stellar cooling. There's also direct detection experiments going on for the dark matter axion. Also, there's a cosmological constraint. So here today's talk is I think focusing on around here, this boundary of the stellar cooling constraints or stellar hints around this region. So here the constraints are something like this. So one of the strongest bound is supernova 1987A. If the coupling is too strong, then the axion cooling is too fast. That contradict with this observation. So that's how the decay constant should be larger than 4 times 10 to 8 GeV in the case of case VZ axion. And there's a similar bound from the neutron star cooling. One of them we obtained some time ago by CAS-A neutron star cooling observation, and the bound is as strong as the supernova bound. So roughly speaking, 10 to 8 GeV is the constraints. But these bounds, both of them are, there are order one uncertainties. So this order one parameter, order one coefficient can have uncertainty, I would say. So that one should keep in mind. Also, there are hints from stellar cooling. So like white dwarfs or other stars, they have, there are some hints or implication that the stellar is cooling, stars are cooling faster than the theory prediction. And one possible explanation is the axion actually is emitted from those stars. And the combined analysis by them show that the FA, the axion decay constant of order a little bit below 10 to 8 GeV can explain these stellar coolings. So you see this number is already in tension with the supernova bound. So here I quoted the number without supernova bound. So it's a sort of boundary or a slight tension with this the bound. But anyway, the axion with the coupling around these values are interesting. So it would be nice if there is a more direct way of probing axions from these stellar objects. And supernova, next nearby supernova, may be such a candidate. Okay, so now I finished this mini review of the axion and now go to the main part. Is there any question so far? Okay, now then I talk about so the main part is very simple. The story is very simple. Only at the end, this event number, we have some equations, but other parts are, I think, very simple story. So there are some nearby supernova progenitors. They are the candidates that may cause the supernova in near or far future. So one of them is, for instance, Antares, which is as far as 170 parsec from us, or Betelgeuse, 200 parsec from us. So there are some these candidates. And if we restrict the candidates to be as close as 250 parsec, so at the end, if it's too far, the axion number is too small. So we chose the closer candidates. And also we restrict the candidates to be only with the mass larger than 10 times the solar mass. So I will explain the reason for this bound later. But anyway, if we concentrate on these candidates, then only 6 candidates are there. So the like speaker is the closest one, 77 parsec from us, or Antares 170, or Betelgeuse 200 parsecs. So these are the targets of the possible supernova axion observations. So these gray dots are the their mass is larger than 10 solar mass, but it's farther than 250 parsec. So maybe in the far future they can be also the candidates of the supernova axion, but for the moment we concentrate on these 6 candidates. And the distance is around here, less than a few hundred parsec.
Can I ask one quick question?
Yeah.
So what is the difference between the blue and red points there?
Blue supergiant, red supergiant.
Okay. Thanks.
Yeah. So yeah, and I don't know actually the detail, but the red supergiants are usually considered to be the supernova candidates, but we also included the blue ones because, for instance, supernova 1987A itself was the blue supergiants. So these blue ones are also a candidate.
Yeah, thanks.
Okay, now let's discuss this Supernova-scope thing. So suppose that some point in near future, one of them really goes to supernova. Then actually before this light comes, there's a supernova burst. And huge number of neutrinos are produced by the a supernova. And many of them will arrive at the Earth. And that actually happened in the case of supernova 1987A. And as I said, there's a neutrino burst within the time scale of order 10 seconds, like this. So that can be, of course, done again. Now, not only the Kamiokande, but many neutrino experiments can detect such a neutrino burst. So that's already very exciting. But here we want to discuss something else, the axion. So if the axion really exists as a solution to the strong CP problem, then they are also produced by the supernova. And so typical or dominant process is this kind of Bremsstrahlung. The neutron proton scattering can create axion. And recall that the axion coupling is inversely proportional to the FA up to these model-dependent parameters. But anyway, given the FA, there's some certain strength of the axion couplings, and they are produced. And then, like neutrinos, many of them also arrive at the Earth. Then it would be nice if we can detect such a supernova axion, not only the neutrinos, but also the axions. And one interesting possibility is to the axion scope or strong magnetic field. So because of the axion coupling to photon, also I should say that at the time of the production, the important coupling is the coupling to proton and neutron. But now for the detection, the axion photon coupling is important. So because of the axion photon coupling, the FF tilde coupling under the strong magnetic field, axion can be converted to the photon. And in such a way, if you put a certain detector, then one can, in principle, detect such a photon converted from axion under strong magnetic field. So, but if you know the axion helioscope for the solar axion, you might think it's the same. And actually, it's the same, essentially the same as the axion helioscope. So the axion helioscope is the experiment to search for the solar axion. So the axions are also produced from the sun, and if they exist, and then under strong magnetic field, it can be converted to the photon, and it can be detected. And this solar axion search has been already done by some experiments, and one of them is the CAST. So far, the strongest one, placed at sun and with 9 Tesla magnetic field and over a 10-meter length and this cross-section area. And there are some next generation experiments like IAXO, planned at DAISY, like this one. So you might think that, okay, then why not just use this helioscope and can use just also for the supernova axion. But there's one problem that the energy is different. So in the case of solar axion, the axion typical energy is keV. So the helioscope experiments are using X-ray optics, X-ray detector with the focusing optics to search for the solar axion. On the other hand, the supernova axion, if they really come, the energy is of order 10 or 100 MeV, simply because the temperature is much higher. So then we would need a gamma ray detector, not X-ray detector. So if we would use X-ray detector for this supernova axion, first of all, this X-ray focusing optics doesn't work because the energy is too high. And even if the axion, the photon is arrived at this detector, the energy measurement is difficult. And the energy measurement is one of the important ingredients to reject the backgrounds. So it would be better to have a additional different gamma ray detector specific for the supernova axion. So on the one hand, we already have an X-ray detector planned or ongoing for the helioscope solar axion. On the other hand, for the supernova axion, we want to have a gamma ray detector. So our idea is to put the gamma ray detector at the opposite end to the X-ray detector. Then, so if we have two detectors in the two sides of this magnetic coil. Then in the normal operation time, it just works as an axion helioscope. So this gamma ray detector part doesn't do anything. Axion just go through. So it's just nothing. So axion goes through here and then maybe converted to the photon by strong magnetic field and can be detected by the X-ray detector. And as originally planned, as an helioscope, it can just follow the motion of the sun and try to see the solar axion. So this is just the solar axion experiment as originally planned. But once supernova occurs, then we can turn around the detector and then point the detector towards the supernova. Now, in this situation, this X-ray optics has nothing to do with the detection. It's just doing nothing. Axion just goes through this part and then convert it to the photon by the magnetic field. And then now this gamma ray detector can probe the supernova axion. So this is the idea of the Supernova-scope. So basically just an helioscope, but put an additional detector specific for the supernova axion. All right, very simple, I think. So now I want to discuss the pre-supernova neutrino. So one problem is that supernova scope has to be pointed to the exploding supernova because the time scale is just 10 seconds, like neutrino burst. So that we have a chance of only 10 seconds to see such a burst of the supernova axions. But if you want to do the solar axion experiments in the normal operation time and only small, only if the supernova occurs, turn around to the supernova, target to the supernova, then we would have to know the timing when the supernova occurs in advance. And actually this is possible with the help of supernova, pre-supernova neutrino. So this is the timeline of the supernova. The x-axis is the time. So this 0 corresponds to the core collapse of the supernova. And the y-axis is the neutrino luminosity. So you see that there's a huge jump of the neutrino flux at the time of the core collapse, and a few seconds or 10 seconds is a large number of neutrino flux. This is the supernova burst, supernova neutrino burst. And note that the supernova itself, in the usual sense, is hours or days after this neutrino burst. So what we see, the explosion by the photon is much later. But anyway, the neutrino burst occurs at this stage. And axion is also in the same timing. So both neutrinos and possibly axions come in this short time, 10 seconds or so. And now, before this explosion or core collapse, actually there is a pre-super neutrino here. So although the flux is much less than this neutrino burst, its flux is continuously increasing towards the timing of the core collapse. So like before 10 seconds or several hours or even days before, the neutrino flux continues to increase towards this core collapse timing because of the evolution of the star at the end. So this pre-supernova neutrino has been studied. For instance, there's a nice review in this paper, and they can be used to know in advance the supernova when it happens. So these are the neutrino number, cumulative numbers of expected pre-supernova neutrino events for ion core progenitor with a distance of 200 parsecs. So like Betelgeuse. And this x-axis is the time to collapse. So these are before this core collapse. And the y-axis is the number of neutrino events, which can be seen by Super K, Camland, Hyper K, or Juno. So the Hyper K Juno are, of course, the planned one, not yet. So you see the numbers can be tens or even hundreds, depending on the timing. For instance, in Camland, let's say 1 hour before the explosion, around here, the number can be as large as several tenths. And compared to the background, this can be large enough to see already in excess. So hours or 1 hour before or even before the supernova collapse, due to the excess of the neutrino events, we can say something is going and maybe the supernova really occurs. So it depends on the mass of the progenitor and also the hierarchy of the neutrino, normal or inverted. And there's a nice system called Supernova Early Warning System. This is a global network for an early supernova alarm. So by combining these information from many detectors, not only them, but also Dune or Snow or many others, there's a system to trigger alarm above some threshold that somehow maybe the supernova occurs soon. And according to their study, the pre-supernova neutrino can be detected above threshold and triggering warning alert hours or days before the supernova explosion for the progenitor closer than a few hundred parsec. So therefore, there's a chance that we really know the when roughly it happens, and there's a chance that we can really point the detector towards the exploding supernova. So there's one minor comment that this supernova progenitors with mass less than 10 solar mass According to their study, this paper, those candidates give only very small flux, neutrino flux, and it is difficult to detect them, even for very close progenitor candidates. So that's why we discard relatively light progenitors and concentrate on heavier guys, because otherwise we cannot know the pre-supernova neutrino a lot. Another interesting point is that it is difficult, but in principle possible, to estimate the location of the supernova candidate on the sky by using the information of this neutrino event. So this is the case for Juno, the scintillator. So for Betelgeuse, the 200 parsec away from the Earth, 1 hour before the core collapse, we know we may be able to know where these neutrinos are coming from, and within 68% confidence level, we can say probably it's coming from this area on the sky. And if you put additional lithium to improve the detector, then one can all narrow down this range. So there is a chance really that before the explosion, we not only know the timing, but also the position or candidate of the supernova, which one is really going to the supernova. So of course, it depends on which candidate. If those two close guys are maybe difficult to distinguish, but for instance, in the case of Betelgeuse, maybe it's easier. So depending on the direction, we maybe really identify one, or otherwise we bet, let's say, just bet one of them or something like that. Also, the flux itself can help to discriminate the candidates, because the flux depends on the distance to the supernova. So now, with the help of pre-supernova neutrino, as I said, this in the normal operation time, it works as a helioscope, and then once this alert is received, and okay, maybe some of them or one of them goes to supernova, then this Supernova-scope can be work as a Supernova-scope towards pointing to the supernova and wait for the axion event. Okay. Yeah. Now, I want to talk one more technical thing, the observational time fraction of the supernova scope. So this is again the IAXO, the picture. So in the horizontal direction, it can rotate, the planet can rotate on 2 pi, 360 degrees. But in the vertical direction, it can only move a certain range from minus 25 degrees to plus 25 degrees in the case of IAXO, or a little bit smaller for the taste. Another plant helioscope. So this is fine for the solar axion, but for the supernova scope, it may not be sufficient. So for instance, if we will know that this supernova is exploding and then the detector is, let's say, here, then in this kind of situation, it can receive the axion event. But since the Earth is rotating, if it's like this, then it cannot be pointed towards the exploding supernova, because of it is a finite elevation range. So we wanted to know how much time fraction really this one specific detector can be pointed to the each progenitor candidates. So yeah, in this case, even if the axion comes, it will miss the event. So this is the this figure shows the altitude of progenitors seen from Hamburg, because IAXO is planned to be built in Hamburg-Tesi. So this theta Sn is the altitude or height of the candidate star seen from specific point, in this case in Hamburg, as a function of the time. So this height can be easily calculated. I mean, this is the geometry. The coordinate is Z is the Earth axis. This is a star progenitor. This is a detector, and the latitude is fixed, but the longitude depends on the time because of the Earth rotation. And then depending on the time, this height of the star is changing. So this x-axis corresponds to this Earth rotation, 24 hours, and this is y-axis is the altitude of the progenitors, and these lines show the position of the star, height of the star, depending on the time. And so this theta max plus minus 25 degrees is the case for the IAXO. So for instance, this Betelgeuse, the red line, for instance, here and here, the helioscope can be pointed to the star, but in this timing and this time, it's outside of the maximum elevation range. And also the other lines are similar. So we see that from this figure, observational time fraction is larger than 50%. So I mean, if there's a 50%, more than 50% of the chance that the detector can be pointed to one of or each of these stars, except for this green one, alpha Lupi. There's one thing it's difficult to see, but otherwise there's a chance, good chance that we can really point the detector. And but there's a chance that we will miss. So if we really don't want to miss such a rare event, then in principle we can do improve the situation. One possibility is simply increase the maximum elevation, theta max. So by changing the maximum elevation from 25 degrees to 50 degrees, the band, so this y-x-axis is again the 24 hours, and each line band corresponds to the timing that the helioscope can be pointed to those candidate stars. And dark blue are the case of 25 degrees, and light blues are the case for 50 degrees. So by increasing the elevation, maximum elevation, of course the time fraction increases. And moreover, if you put additional detector to different longitude, let's say, just to give an example, Tokyo, then you see there's some complementarity that by placing two detectors, now it's always possible to point one of the detectors to each of the progenitors. So in the case of 50 degrees elevation plus two detectors in different places, there's a 100% coverage. So it's always possible to at least one of them point to the possibly exploding supernova. Yeah, so that's one thing, but there's a chance that we can really point the detector. Okay, now finally, maybe I finished a little early, but anyway, finally let's count an event number. This is, I think, the most important part, possibly the event number. So this is actually also simple, that the total number of events at the detector is simply the number of events produced by supernova times the solid angle fraction times the conversion probability of axion to photon at the detector. So the production, solid angle, and the detector. So the most complicated and uncertain part is the production part. So as I said, the dominant process is this one pion exchange Bremsstrahlung, and also the coupling we know given the model, but still there are many difficult parts like finite density or other corrections. And we simply follow the latest, one of the latest calculations by this paper, which this study includes the various corrections to the simple one pion exchange approximation for the production of the axion, like finite pion mass or low meson contribution and so on. And we just used this fitting formula for the axion luminosity. This is the luminosity at the time of post bounce 1 second. So after quark collapse, 1 second after the quark collapse. But within 10 seconds or so, the luminosity doesn't change much. So we just use this number. So it's of course inversely proportional to the FA squared because coupling is inversely proportional to FA. And there's a order one fitting formula for the neutron proton coupling combination. But yeah, otherwise it's a simple formula. And we also include the temperature dependence or temperature uncertainty, which we read from the formula to be T to the power of 5/2. So there's a dependence or uncertainty coming from the temperature of this power. This also gives the order one uncertainty to the final number. The axion energy is in terms of temperature, it's rather stable. So this figure, maybe it's sorry too small, but the x-axis is the energy of the axion in terms of temperature. Y-axis is the flux, and the various lines corresponds to various approximations or models or medium corrections. But you see that it's doesn't change much. So the axion energy is rather how to say well known in terms of the temperature. So we took this number for the axion energy. Then once we know the luminosity and the energy, by dividing the luminosity by the energy, we know the axion production rate. And by multiplying the time, which we took 10 seconds, because this is also this is basically the same as the neutrino path. So within 10 seconds, the most of the energies are released. And for this order one coefficient as a representative value, we took the KSVZ number. And for decay constant, we took 10 to 8 GeV order. This is in some sense the boundary of the constraints. Then by plugging these numbers, we get 10 to 57. So these are really huge number of axions can be produced from a single supernova explosion, like the case of the neutrino. Then the second factor is simple, simply because it's far distance. D is let's say a few hundred parsec, depending on the progenitor. And then this A is simply the area or cross-section of the detector. And here the same table as before, but in the case of, for instance, the IAXO, this cross-section is 2.3 meters squared. So there's a huge reduction, of course, because the solid angle is so small. Only a small fraction of the axions will arrive at the Earth and arrive at the detector. But still number, this 10 to minus 39 is, this original number is very large. So these there are still can be huge number of axions can arrive at the detector. And finally, this axion photon conversion probability, this is also very well known. It's essentially the coupling times magnetic fields times the length of the detector overall squared up to this suppression factor. So it's essentially the oscillation process, and as far as this the length is less than one oscillation length, we can forget about this factor. It's one unity. And then again, putting typical numbers of this is the same as before, the 10 to 8 GeV decay constant, and photon coupling parameter again taken to be KSVZ typical value, and magnetic field again taken from IAXO 2.5 Tesla, length 20 meter again from IAXO, then probability is 10 to minus 20. So it's not so large, but still there is a finite chance of the axion photon conversion in this supernova scope or helioscope. So here the suppression factor is due to the oscillation. If the mass is too heavy or length is too large, then the axion photon starts to oscillate, and therefore this factor makes a suppression factor. Okay, then by combining these three factors together, at the end we get this equation. So there's a factor from the axion model. So FA we took 10 to 8 GeV order, and there's an order 1 coefficient from depending on the axion model. And then there's a numbers from supernova, depends of course on the distance, depends on the duration of the burst and the temperature. And then there's a detector values like cross section, the magnetic field, and the length. These are that we took from the IAXO as a representative value, and possible suppression factor if the mass is large. So I should emphasize this. So at the end it becomes 1 just by accident. So we hope order 1 axion event can be detected with these representative values. But we also should know that is a rather large uncertainty in this number. Can be not on just order 1, but order of magnitude uncertainty can be there, especially from supernova part. Not just the temperature, but the original luminosity formula itself assumes many things. So there can be a large corrections to this formula. So yeah, it can be larger or smaller by order of magnitude. So this equation now we can show in a figure. This x-axis is the axion mass, y-axis is the axion photon coupling, and this blue shaded region is already excluded by the cast experiment, and orange and green shaded regions can be covered by the future planned experiments, helioscope experiments. And these blue and red lines are the sensitivity of the Supernova-scope. So the blue one is a speaker, the closest one, 77 parsec, and red one is Betelgeuse, 200 parsec, the farthest among the 6 candidates. Here we took the order 1 parameters to be the KSVZ parameters, whereas axion mass is taken to be free parameter, because otherwise it just becomes line in case VZ and DFSG models are along this line. But in this figure, we just take the axion mass to be free, like axion-like particle plots. So you see that in the larger mass region, like 1 electron volt, the sensitivity is better than the helioscopes. So helioscope, the sensitivity becomes worse around of order 10 milli electron volt around here. This is because the energy of the solar axion is over the keV. But in the case of supernova axion, it's much energy is much larger, and therefore the suppression factor doesn't work up to a larger mass. So maybe I can show this factor. So the larger energy case, the suppression factor doesn't suppress up to larger mass axion mass. So that's why it extends to around up to this region. So this is one thing. And another thing is that for smaller mass region, maybe the both solar axion and supernova axion, both of them, in the most optimistic case, may be discovered. Okay, finally, I should comment on the constraints. Actually, in this figure, we didn't show the stellar cooling constraints. This star corresponds to stellar cooling hint, but otherwise we didn't show the constraints from the neutron star and in supernova 1987A. And in this figure, it's shown. X-axis is the axion coupling to proton neutron, and y-axis is the axion coupling to photon. And here we fix the axion mass to be -3 electron volts. And as I said, this axion, supernova axion sensitivity is both sensitive to the photon coupling and nucleon coupling. So that's why it goes to this direction. So Betelgeuse 100 events and Spica 1 event. On the other hand, stellar cooling constraints from neutron star and supernova 1987A is constraint on nucleon coupling, and it actually here. So the coupling above this value is constrained. So if we really take this bound seriously, then the crossing point, for instance, KSVZ and this bound is just marginally gives one event for Spica. So it's in some sense the constraints and the supernova axion sensitivity is a slight tension in some sense. Maybe it's, if you really take these values seriously, maybe it's difficult. However, as I said, there's an uncertainty for the stellar constraints or stellar cooling constraints. So there's a chance that the number can be increased. So just to parameterize one of them, here shows the dependence on the such an uncertainty. So this C error parameterizes the axion luminosity relative to the formula used in the calculation. So if the real luminosity is larger or smaller than the formula by this factor C error, then the sensitivity curve is changing as a function of this uncertainty. The FA sensitivity is changing, and constraint is proportional to this C error of power of 1/2 because of it's only constrained the production. Production is 1/FA². On the other hand, a Supernova-scope sensitivity is proportional to such an uncertainty of power of 1/4 because both production and detection uses a vertex 1/FA. So because of the difference of the dependence, it can happen that depending on this error, the possible number is increasing. So if, for instance, this uncertainty error parameter is of order 0.1, then even if we take seriously this supernova bound, order 1 event is possible for Betelgeuse or order 10 events for the Spica. Okay, finally, I briefly talk about possible detector design and background, possible backgrounds. So as I said, we want to put a gamma ray detector at the opposite end to this helioscope. And one possible design is like this. So we can put CSI plates, many of them, like several tens of layers, and to see the gamma ray. And we can also put a plastic scintillator around such a gamma ray detector to reject the muon background. Actually, the largest backgrounds we think is the muon. And within a time window of 10 seconds, over 1,000 muons go through with such an gamma ray detector. But those coming from the site simply can be vetoed by this plastic scintillator. And even if it comes from above, like the signal, we think they can be rather easily rejected by energy deposit and the number of hits. So these two are the simulations showing the signal and background. So the energy deposit is very different. The signal and the backgrounds are very different. Also, the number of hits of this scintillator is different. So this is a histogram for muon. So in the case of muon, essentially all the it goes through all the CSI detector, whereas in the case of signal photon, they are stopped. Only part of those detectors are hit. So that's how this is a logarithmic scale. So it's very easy to distinguish the background and signal by this kind of simple setup. Of course, in a realistic setup, I think we should think more carefully. But just by thinking this simple setup, we think the background rejection is not a big problem. So really, order one event can become really the signal. Okay, so this is the summary slide, the same slide as I showed at the beginning. So the main message is that if nearby supernova occurs, maybe many axions may arrive at the Earth together with neutrinos, and such supernova axions may be detected by this kind of setup, Supernova-scope, with the help of pre-supernova neutrino alert. And such a Supernova-scope based on something like IAXO can potentially detect order 1 or order 10 supernova axions. So in any case, nearby supernova is so rare. It's I think one in several decades in the whole galaxy or something. So maybe most likely we won't see such a nearby supernova anyway. But if it really happens, it will be a once in a lifetime opportunity to study many things, and maybe we can also study the axion from such a supernova. So thank you very much. That's
Thank you very much, Koichi, for very clear and interesting talk. So we have time for questions. Who wants to go first? You can just speak up or raise your hand. Maybe, yeah, Kieran, you start.
Yeah, thank you for the nice talk. I wondered about if there are any supernova where it would be conceivable to have a decent enough flux of ALPS or axion or QCD axions from a single coupling. So say, for example, just taking the photon coupling. Is
not
it
combination
enough of a flux from just like a Primakov? Or is it just going to be negligible compared to the potential like nucleon Bremsstrahlung?
Yeah, I think it's so. This is already the most optimistic case, and using both the nucleon coupling and photon coupling, and the photon coupling only, I think, would give much smaller event axion from a supernova. So in that sense, a single coupling is much more difficult to probe. Is it answering your question?
Yeah. I just wondered. Yeah.
So for instance, the solar axion, just the photon coupling is sometimes enough, like this xenon-1-ton interpretation. But in the supernova case, yeah, nucleon coupling is necessary.
Can I ask one question? So
Yeah.
how well do you have to point your supernova scope to the supernova? To what angle of degree do you have to point it to the supernova such that you can actually get the signal?
Yeah, so we also thought a little bit worried about, but if you see the numbers, it is area, cross-section area is like meters length, and the total length is 10 meter. So the angle of this rectangle is like 0.1, so not so bad. So if we can target within this range, it can go through the magnetic field.
Okay, that makes sense. That's I was worried about that, or I was concerned.
We also worried about that. Yeah.
So a question related to Mikhail's is how quickly could the detector be slewed around and then azimuth? So you have to slew, and then you have to change also the azimuth, and you might have a lead time of minutes at best, depending on the yield. So how quickly can this be done?
Yeah, we tried, but we haven't explicitly checked the maximum speed. But at least they can follow the motion of the sun.
No, that's clear. That I understand.
Yeah.
That's not
but within a few minutes. Also, I don't know. I don't know. We haven't checked that.
Because I've not looked at this independently, obviously, but just based on the numbers that you showed, the case for suspecting that a supernova is about to go off somewhere in the sky is much stronger than the case for knowing that a supernova is going to go off right there. So, I mean, you could be focusing on a hemisphere or guessing between 2 or 3 candidates, but it seems very chancy to think that you could focus on one candidate that you could a day or 3 hours before, focus directly at one definite candidate. It seems much more likely that you would be having to respond quickly to
closest one
just before collapse. Yes.
Yeah, but sorry, I don't have the clear answer. Yeah, we haven't checked the speed.
Because the directional information seemed quite poor.
Right. Yeah. This study is most optimistic, and actually one of our collaborators in experimentalist say this is very optimistic, and it's very difficult to really point the direction. Yeah.
But most of these stars you can see with the naked eye. I don't really know what a star looks like when it's about to go supernova. Maybe nobody does, but you might be able to just know because you would have seen it.
Yeah, but the thing is
going crazy or something. I don't know.
But no one's ever done that. Is the problem?
Yeah.
If we had that level of knowledge, then there's a whole bunch of things we wouldn't still be speculating about, I think. I mean, what? Iron burning lasts a day?
Yeah.
I think in core collapse, if it reaches iron burning, that lasts a day before the star blows, or even less. I'm trying to remember. The final stage.
I think you see it in like neutrinos or any of these weakly interacting stuff before you see photons at all. I mean, by the time you can actually see it in visible wavelengths, it's already it's done. You see nothing anymore. Yeah.
So what we call supernova is much after.
Yeah, it's days before the photons actually even manage to escape the mantle. So it's already way too late by the time you see it in the visible.
Right. Yeah.
Any other questions? Actually, I have another one. would you learn something if you would have a helioscope or a supernova-scope in the southern hemisphere?
Yeah, we tried, but not much. More important is this longitude difference.
Longitude difference.
Yeah,
so kind of
complementarity.
Okay.
Yeah, like in Australia. Yeah.
Any other questions? No.
I guess I'll ask the sort of meta question. I mean, have you spoken to anyone at IAXO or TASTE about whether or not they are sort of willing to do this?
I'm not so sure. Actually, I sent a message to Andreas Ringvar, but no specific reply. And I don't know, if they receive it seriously or not. Yeah. Maybe the supernova chance itself is too low. I mean, to consider seriously. That's maybe the most, bottleneck, maybe. Yeah.
But I guess the main cost would be that gamma ray detector, which you have to put on the install, which is probably small compared to the magnet and the whole infrastructure.
That's we hope. Yeah.
Good. If there are no more questions at the moment, so then let's thank Koichi once more, and we can finish the